Hi, my name is Jacob Bender, and I'm going to be your guest lecturer today, talking about load computations. This is going to be one of 3 videos overall that I'm doing. We're discussing right now heating load losses. We'll discuss cooling loads later, as well as having another video for your homework examples. My name is Jacob Bender. I'm a local engineer and been working a little bit with Crystal recently, and she asked if I could help share a little bit of the industry knowledge with the class, and I figure I hopefully can help you guys out a little bit and be a resource for providing some real world answers. Fundamentally, heat is going to flow from a hot area of space to a cold area of space. When we introduce insulation between the two, that's going to provide a little bit of a buffer that slows how quickly heat flows between it. We want to be able to calculate that rate of heat loss, so we are able to design a system that can replenish the heat in a space in order to maintain a desired temperature. Sometimes we want to just have occupant comfort. That's what a majority of cases are going to be, making sure that people are able to set a thermostat where they want it to be and keep it. Sometimes it's just simplified for freeze protection, making sure that water lines don't burst, it doesn't get that cold, or the building structure isn't damaged by cold temperatures. There are 3 primary methods by which you're going to have heat loss: transmission, infiltration, and ventilation. For the purposes of everything that we're doing today, and most of what we're doing in the US industry, you're going to be using IP or US customary units, such as BTUs or inches or pounds or things like that, not SI or metric. The closest we're going to get with SI and metric is going to be the use of watts or kilowatts, but primarily related to electric power. You'll see the letter Q being used to note that quantity of heat. Capital Q is your total quantity. Lowercase q is the rate of quantity change. We're noting that in quantities of BTUs or British thermal units. For transmission, everything's dictated by equation. Lowercase q equals UA delta T. U is your U factor, which is determined by insulation. Your A is your square footage or area of exposed surface. And then your delta T is going to be your temperature difference. If you multiply that value, your rate of change by time, then that gives you the total quantity, uppercase Q, that has escaped from the space. On the transmission side, it's important to note the effects that the earth have on the building. Earth, by means of soil, actually conducts heat very well, but it also is able to absorb and store heat, which is slowly released over time. You'll notice this from a practical standpoint on snow days where it may be 26 degrees outside and snow is falling, but if it was 70 degrees 2 days previously, the earth is still maintaining some of that temperature and releasing it, and you can see it snowing all day long and no snow actually sticks to the ground. This generates what's called thermal lag, which means that the earth is slower to respond to overall temperature changes than just a day-to-day basis. This typically impacts the building the most around the perimeter because that's closest to where you have exposed earth getting gains from the sun or your atmospheric temperatures. Infiltration is air leaking in and out of the building in an unplanned manner. There's a lot of factors that go into this, like the temperature difference between inside and outside, wind velocity outside, people opening doors and windows. You know, someone comes in and out of the building and there's a gust of cold air inside. That's not something that is planned, that just happens relatively sporadically. You also have the age of the building that factors in. Older buildings have a few more cracks and gaps between things that allow air to flow back and forth from inside to outside. It's tough to definitively quantify the infiltration. You don't have a Q equals UA delta T precise calculation for that. I tend to use two estimation methods. You can either use crack estimation method, which is where you're actually quantifying the area of known gaps around the building, or you have the air change method, which is approximating the number of air changes per hour for the overall building based on the volume of space inside. Ventilation is a planned component of your overall building structure. That's where we're factoring in fresh air requirements, exhaust requirements, and pressurization requirements. The fresh air is something that is code dictated based on the space type and occupancy, and there's a certain quantity of outdoor air that you are supposed to bring in to be able to cycle out old stale air. This helps prevent buildups of carbon dioxide or gases like that inside the space. But that's something that's going to be introduced typically in conjunction with your heating and air system unit. Exhaust is something that you're going to have required for restrooms. Kitchens are going to have some exhaust quantities. Laboratories have some of that. So we're having a known amount of air that we're intentionally vacating from the space. And we're taking those back into account with a balance between the two. We want the pressurization of the building to be relatively neutral. So we want to be removing approximately the same amount of air that we're introducing, and vice versa. If you have a building too negatively pressurized, the doors and windows might actually be difficult to open because you've got a vacuum inside the space. And likewise, if the building is too positively pressurized, you may have doors that don't really shut. They're kind of blown open by how much air is inside the building. Typically speaking, as an overall building, a slight positive pressurization is good because you're minimizing the amount of infiltration. Air is going to tend to seep out from the space rather than in. But there are particular spaces that you do want to be negatively pressurized themselves, restrooms being one of them. You definitely want the air in that space to be pulled from the outside in, so you don't have whatever gases inside the restroom going out to the rest of the space. When we're looking at heating calculations, we're pretty much only concerned with dry bulb temperature, hot and cold. Humidity doesn't tend to be a really big factor in your winter or cold weather months. The heat loss itself is pretty variable. You're going to have factors, time of day, day of the week, a lot of things that cause that rate to change. The load calcs can vary from a general rule of thumb, such as X amount of BTUs per 1,000 square foot based on the building occupancy type, to more complex modeling calculations. The calculations use recorded historical climate information and interior design conditions to calculate what's happening at given points of time and given accuracy. You do have some heat gain generated inside the building itself, separate from the mechanical system. Lights generate heat, motors generate heat. If you have kitchen equipment, ranges, ovens, even mixers, those all generate heat spontaneously into the space by nature of their usage. Same thing happens with people. Human body temperature is somewhere around 98.6 degrees on average. In a 70-degree space, heat is going to be transferring from human bodies to the space around them. So you're going to be factoring that in as well. That heat gain does take a little bit of the load responsibility off of the heating side of the HVAC equipment, but is a major thing to take into account on the cooling side, which we'll get to later. When you're looking at the overall load calcs, the methods that you're going to use, you're going to have your calculations totaling up your infiltration loads and your ventilation loads. You're going to determine inside versus outside temperatures from a design condition and worst case scenario standpoint. Figure out the U factor of the assemblies of your building exterior, and determine the interior wall area. It's important to note that you're using interior area and not exterior area. The corners of the buildings, you don't have double exposed surfaces, so you're calculating interior point to interior point where those walls are located. And for transmission, you can use the Q equals UA delta T to figure that out and sum that all up together to get your heating load. Overall heating load on a building is going to be equal to the sum of the heating loads for each of the individual spaces. So depending on how the heating system is zoned, you may be running individual loads for specific rooms, one by one, and then adding them all up together to get your overall building loads. You may also be factoring in a little bit of safety factors or room for expansion if a building might have an addition put onto it and they want to have the option of pulling from the existing heating and air system to take care of it. Or they may be at a point in time where if they added something onto the building, they may install a new system specifically for that. So that's something to keep in consideration during the design stage, is future intentions for the building. Your book talks a little bit about estimating energy consumption and operating costs, and some of the homework questions are going to be factored off of that. They'll give you some good numbers to work from. You know, hey, here's what heating cost you should use for this. From real world application standpoint, currently energy costs for various fuels fluctuate heavily, and we've in the past couple of years seen some costs skyrocket and other ones go up and down. So making long-term estimations of what it's going to cost to run equipment can be a little bit dangerous. It's a little bit better to speak in relative cost terms from, you know, this type of heating system is going to cost X dollars more per day than this type of system. There are probably going to be 4 different heating system types that you're likely to encounter in real world operation. Gas heaters, be it natural gas or propane, is one of the cheapest methods of providing heat. But when you're burning fuel, that generates carbon monoxide. If your equipment is located outside the building, that's not really a big deal. But if you've got a lot of interior units that you would have to duct vents from the burners themselves to the exterior, that might make gas not a good option for that particular design system. Electric strip heat is pretty versatile, but electric heat itself tends to be one of the more expensive methods. And that strip heat does have a major impact on your building electrical service size. Heat pumps are a very economical, effective means of generating heat, and it effectively works as a reverse air conditioner. Air conditioner is taking heat inside the building and moving it outside. The heat pump takes heat from outside the building and moves it inside. You may occasionally run across geothermal energy on projects that have a substantial construction budget and owners who are particularly driven by it. It works fundamentally the same as a heat pump, except instead of just getting it from ambient air outside, you're removing heat from typically a well drilled pretty deep down into their surface, deep groundwater levels, where the water is kept at a pretty warm temperature from the heat of the Earth's core, and then bringing that into the space. The upfront costs on that are pretty high, but long-term operating costs, they run very, very cheaply. You're typically going to see somewhere around 3 different calculation methods used. The bin method is kind of looking at everything in bulk, all worst case scenarios happening at the exact same time and sizing based off of that. You do have programs out there that run modeling computation software hour by hour. It's very precise. It'll tell you based on the exact latitude and longitude coordinates of where you are, how the building is facing, what time of day, what time of week is going to have the worst case scenario, and you can plan accordingly. On the heating side, though, there's not really a big problem with units being oversized. You don't want to spend an inordinate amount of money on or for the owner's construction costs on the equipment, but if you've got a building where your heating load is, say, 54,000 BTUs, and the burner that is in your gas furnace, the minimum level that's on that is 80,000 BTUs, that doesn't make as big of a difference. You don't really have a problem oversizing on this the way that you do in cooling systems, which we'll get to in the other video. So doing the hour-by-hour simulation, there's a large time investment and a large investment of effort to make that. And sometimes that may not be your most cost-effective means of determining your loads on the building. The degree day method is a simplified rudimentary method figuring out daily heat loss and using that with your overall loads to estimate the total quantity of loss per day. This is primarily used to give estimations about operating expenses when you combine the heating degree day and loads with your unit efficiency and the fuel costs in dollars. So we'll get into some of our homework questions in the other video dealing with heating degree days and cooling degree days. But as far as the general heating loss lecture goes, that concludes it. You do have your slideshows that go along with this chapter from the book. Feel free to peruse that in conjunction with this and go back for some other technical details that may be there for homework questions. Thank you very much.